Today, we're presenting to you our project, which is the model predictive control-based safe battery charging for lithium iron phosphate batteries. In the industry, constant current, constant voltage, constant current are used more often for charging batteries. They're simple and require less computational costs. However, not optimal for battery health. Under high temperature and current while charging and discharging, the battery degradation is increased significantly and might potentially cause fire. In our project, we'll be using the MPC algorithm to find the optimal charging sequence. This will monitor the factors which cause the degradation in batteries. Also, with the 2RC ECM thermal model, the MPC algorithm we created will find the optimal charging controls that achieves fast charging and safe operation temperature. Since our goal is to improve safety and battery health while charging or discharging, the four major factors that are being considered while designing our MPC are ambient temperature, core temperature, surface temperature, and current. Allow me to pass to my colleague to further discuss our project.
Lithium-based battery cells dominate the spectrum of electrical storage when it comes to portable electronic devices due to the high charge density, high volumetric, and high cell voltage. Having knowledge of the state of charge and the state of health allows damage prevention, safety insurance, minimal charge time, and the maximal battery life. The purpose of this study is to design an MPC controller for the equivalent circuit model as the charging sequence instead of the traditional charging. The optimal charging profile is applied over a moving horizon following a modified classical MPC approach. It's implemented in the Python library. The only available measurement for a Li-ion battery are the voltage, current, and temperature. But the state of charge and the state of health need to be estimated. The state of health equation is nonlinear, and its value is arbitrarily small for Python to compute. So the state of health is removed from our calculations due to the complexity. In our study, we will utilize the optimal temperature and the difference between the current state of charge and the state of charge at the terminal state as our control target of the MPC. The goal is to keep the battery core and the surface temperature low during degradation of the battery.
The 2RC ECM model is used to represent the battery's electrical behavior, and the lumped thermal model is used to represent the battery's thermal behavior with respect to its surroundings. We have three states in the 2RC ECM model, which are state of charge SOC and diffusion voltages V1 and V2. And there are two states in the thermal model, the battery's core temperature TC and surface temperature TS. TF is ambient temperature, and in this project, we manually control TF to see the battery MPC model's reaction to the changing ambient temperature. The parameters used in the project can be found in the table on the left side. In reality, most of the parameters are a function of temperature. However, they are assumed to be constants for simplicity and the purpose of the MPC model in this project.
The MPC formulation we do is very classical, however, it has its nonlinear deviations. When creating our cost function, we want to minimize three key aspects of the system: state of charge, battery temperature, and current. The most important aspect is the core and surface temperature because it relates to the battery's health and environmental safety. The last two states, TC and TS, are the only ones that need to be minimized, which we can see in the queue. The rest of the state multipliers are set to 0 because the capacitive voltage and the state of charge should not be minimized. Second is the state of charge because that makes sure our state of charge hits our desired value sooner, and the cost function reflects this. The P is our tuner to impact that rate. Finally, we want to minimize current, but understand that current has less impact than temperature regarding the state of health of the battery. We choose our constraints based on reality. I will mention some important factors in deciding the constraints. 1. State of charge is constrained to protect the battery health and the risk of overcharge, which creates a fire hazard. 2. The capacitive voltage constraints are not so important because the voltages typically are small. 3. Constraints for battery temperature is limited to 45 degrees with 10 degrees buffer because that is where fatal battery degradation begins. 4. Our battery temperatures start at ambient temperature. 5. The final values do not matter as long as they're within the safety constraints except for the state of charge. 6. The battery model described in the previous slide can be discretized. Since we have a nonlinear model, we understand that some linear techniques aren't available to us, such as creating invariant fields for a horizon size. But what we ended up doing was to test the horizon side empirically for different scenarios and see which one works best. The system is stable because the cost function, which is based on the Lyapunov function of the system. We can see more about the monotonic decrease in the next section of our results.
Let's look at the figure 5.1 at the top left corner. we see the effect of charging the battery during different constant ambient temperatures. So, as we increase the current, the core and surface temperatures, red and blue, of the battery increase. The core temperature is the highest since that is where all the heat is generated. However, as the current decreases, core and surface temperatures go down until an equal steady state condition is reached, which is the ambient temperature. In figure 5.2, it can be seen that for constant ambient temperatures, as we increase the ambient air temperature, the batteries get charged more slowly, since at each time step, the state of charge is lower for higher TF values. The MPC realizes the lower temperature, and then a higher current is applied to the system, which makes the charging process quicker. The overall current is exponentially decreasing as a function of time. The battery MPC model is adjusting the amount of current given to the system based on the ambient temperature. As shown in the figure, the lower the ambient temperature is initially, the higher the current is applied by the MPC algorithm. In figure 5.3, as the ambient temperature is increasing, the ambient air is heating up the battery, and when the ambient temperature is decreasing, it is cooling the battery. The initial rate of increase of TF is high enough that even though there is heat generation due to high current in the core, it is still below that of the ambient. We actually see the same behavior in figure 5.4 as in figure 5.3, except for the following differences. Now we have 3 cycles, and in each of those we have sudden drops in TF. Even though we see a sudden drop in the ambient and surface temperatures, the core temperature is responding well due to the MPC algorithm. Later, we witness that the surface temperature follows the core temperature trend in figure 5.4 as per the MPC model. Cost trends are shown on the right side. In figure 5.5, cost trends are monotonically decreasing, showing that the system is asymptotically stable and the cost function is a Lyapunov function of the system. Cost trends in figure 5.6 are following TF trend. As TF increases, core and surface temperatures increase following TF, so more cost is required to push down TC and TS. This implies that when TF takes a place in, the cost highly depends on TF, and the system is not asymptotically stable anymore.
Since we are using MPC, we are able to better handle unknown changes in our system as seen from the previous plots. If we were to only optimize the system once in the beginning, unknown changes in ambient temperature could not be accounted for, which could result in catastrophic failures. For future developments, we can set the ambient temperature as one of our decision variables, and thus we would give a certain temperature range to the battery, and then control the cooling system and current for optimal charging, considering the health status of the battery. Another improvement we can do is to linearize our system by applying certain mathematical techniques obtained from other research papers about linearization for nonlinear models, which would allow us to incorporate more complex nonlinear equations and terms, such as the state of health, by linearizing them. Here are the references. Thank you for listening. Hope you liked it.